You ready? Can you hear me? Yeah, okay. So, hi everyone. I'm Filip. I work as a DevSecOps engineer for Marlink. And today I'm going to talk to you about vector search in SOC environments. First, we are going to review traditional search methods. Then we are going to review some theory on vector search, and then try to investigate an attack scenario together using vector search. So traditionally, what we do in SOC environments, we do some kind of lexical search, which relies heavily on keyword matching, regular expressions, and performs badly on raw and non-standardized data, and usually requires some data parsing. Also, when we try to search for stuff or detect stuff, it's susceptible to small changes in attacker behaviors. For instance, difference in small and big letters can break our search or detection. So let's see what vector search has to offer us. Vector search is supposed to enable us to search by meaning, which is semantic search. In this case, search text as well as the query becomes a vector, which is created by a machine learning model. Then match is created based on distance in n-dimensional vector space. And it's suitable to run on raw data, as we will see later in examples. So generally, we can say that there are dense and sparse vectors. Just briefly, dense vectors are fixed length, while sparse vectors ditch zero values, so are more resource efficient. Dense vectors dense vectors produced by this kind of models. These models require to be trained on more specific data to the domain that we are using it. And sparse vectors can generalize well without extra fine-tuning. If we try to look at the vectors, they are just, in the case of on the right side is dense vector, just a bunch of values. Every one of these values are some kind of relation to, they try to describe relation to the feature of the data. On the left side, you can see a sparse vector created by elastic CLCR model. As we can see, these are the key value pairs. We can try to recognize some terms and the weights assigned to them. So what happens when we try to do a vector search? In case of dense vector matching, the ultimate goal is to find the nearest neighboring vector to the query vector. And this picture represents that well. If this is the vector space, we can see that the search for an apple is going to be close in vector space to apple as a fruit and to apple as a company, which is a good and a bad thing because it's not like fruits are related to the Google or Apple as an IT company. But we'll see later in example exactly something like this case. In case of sparse vector matching, this is the case specifically for elastic CLCR model. So input text and the query are passed through the sparse encoder model. They do some kind of term expansion and synonym expansion, assigned weights, and then when you try to match it, these weights, they do a dot product, add it together, and you get the score. And then the highest scoring document is returned at top. So let's get practical. I'm just going to show you briefly how easy it is to set this up in Elasticsearch. So after you pick the model that you want to use, you can use eland import hub model tool by Elastic to import the model to your Elasticsearch instance. After that, you have to configure the right data mappings for dense vector or sparse vector, and then add your ingest pipelines to process the input data and create vector from the input logs. Now I created one attack scenario that we are going to investigate together. So we get a call from besides Zagreb organizers, and they reported that their threat intelligence saw their super secret file leaked and offered for sale on dark web forums. And they provide us with CloudTrail and application load balancer logs ingested in Elasticsearch. So let's try to investigate this together. So this is my Jupyter notebook, and the first thing here is just some connection initialization to Elasticsearch. First step, we can create hypothesis that this file was leaked from an S3 bucket, which is not uncommon thing. And in first example, we use k-nearest neighbor search with data that's processed with secure BERT models. So this is actually a model that's trained on a bunch of data related to security. And we will try to search freely. So we don't care about format of the data or what's inside the logs. We will try to extract the meaning. So the meaning is that someone got the object from S3 bucket with name besides Zagreb. So if we look at the results, what we can see that we get a bunch of get object calls to an S3 bucket, but it's the wrong bucket. All of these top 15, I think, logs are related to getting an object from a CloudTrail bucket. And this is very common with dense vector matching, as we saw earlier. We might get, for searching for an apple, we might get an apple as a company and also apple as a fruit, or maybe even bananas, because they are close in vector space. So here are some other queries that I also try to use, but they perform badly. I would not say that they performed badly, but the results were not correct. So let's switch to the sparse vector model, in this case, ElasticSEAL-CR model, and use exactly the same query. And then in top 3 results, we can see that Lambda S3 user got object from the bucket named besides Zagreb, and he got the super secret text file. Okay, so we found the file, we found a way how it was grabbed. We can see also some list object actions on the same bucket. But if we try to find more stuff related to Lambda S3 user, we couldn't find anything. This indicates that an attacker escalated their privileges to this user and knew specifically about this bucket and went straight to listing it and grabbing the file. Name of this S3 of this user that grabbed the file indicates that it is somehow related to a Lambda function. So let's try to fairly search for any kind of, and we know that Lambda functions often can leak can leak credentials, either hard-coded in the code or through the environment variables, and try to get if someone tried to get Lambda function, and we say that user agent is both a core, because with this, as we saw here, we can get someone using AWS CLI. And we can see that in top results, we get again these things related to the S3 bucket. These things got really high scores, so they surpassed the actual get function, which maybe is related to the fact that the get function call is not called exactly get function, but they have a suffix of year and month and the date. But here we can see that we can see that the function name S3 retriever was grabbed via the AWS CLI from some IP address. And the user used here is the AWS assumed role. And from the ARN, we can see that this is the role that's related to an EC2 instance. And the way to achieve this is to use instance metadata service. If we try to find anything more related to this instance, because what we can get from here is this role IP address, but let's not stick with the IP address and the instance ID. We couldn't really find anything. So here we try to get the metadata related to this S3 Lambda role. And actually, CloudTrail doesn't catch this stuff at all. So let's pivot to application load balancer logs for more info. Here again, we have a completely, so the CloudTrail logs are JSON format. And here we have a completely different format. This is something like space delimited values. And again, we are doing a query on this raw data. I try to freely query for metadata IAM S3 Lambda. And here we can get requests to the vulnap ALB and passing a request to the instance metadata service. You can see from the IP metadata and then related to this role. We can also see put request for getting the token for the version 2. And now, so we can confirm that this was exploited. This is the SSRF. This SSRF vulnerability was exploited. And let's try to confirm that this is actually connected to the instance that we identified earlier. And let's get back to CloudTrail logs. And let's say search. I forgot to say. Here from the target group, we can see the name of the target group of this load balancer. So if we search for the target group and the instance ID, what we find in top result is a root user adding this instance ID that we saw earlier to this target group. So that's it. I think we helped the guys from B sides. Let me get back to presentation to draw some conclusions. So we can see that vector search can be effectively used for security analytics. It can lower onboarding time with new types of logs. So we didn't have to parse anything. We didn't have to know and care actually if it's a JSON format or some other kind of format. Sparse vectors, as we saw, we used actually, not sure if I mentioned, but we used sparse vector search all the way from the first example and to the end. It brings better out-of-the-box results because I didn't bother much with picking the right model and so on. Dense vectors require to be trained on more relevant data. So despite that this model was trained on some kind of security data, obviously it needed more specific training on, let's say, logs from CloudTrail. If we talk about using this for detection rules, we can say that it's actually sensitive to similar values. So it might require a lot of tuning, maybe some kind of hybrid search that Elasticsearch supports. And for further research, I would like to see the impact of retrieval augmented generation and semantic re-ranking on search accuracy. That's it. Thank you. Any questions?
Test. Okay. Do you have any questions? Yeah. Ilya, do you have yours question? Are you sure? Yeah, just now. Try it.
Blah, blah. Okay. Yeah, thank you for the presentation. It's a really cool idea actually to use like a vector search to search the logs. Kind of seems like a future of it maybe for some other use cases, not just security.
Yeah.
But my question is, how do these specialized models for security compare to more generalized stuff from OpenAI, for example, with the embeddings and stuff like that? Have you maybe tried that stuff?
Well, first of all, there are a lot of limitations with dense vector search because it's more resource intensive, and you can see from the first example. This is specifically in Elasticsearch. You have to limit the maximum number of candidates per shard. So data is, if we get into Elasticsearch internals, data is divided in shards. And this option is, the maximum value that you can set here is 10,000. And it's 10,000 per shard. So if you have more data, this is going to be even more approximate. It's not going to pass through all of the values. Also, resource-wise, storage-wise, it asks for much more than sparse vector search. So for now, I think that sparse vector search might be better, but I haven't tried GPT models or something like that.
Cool, thank you.
Any other questions? Yeah.
Oh, it's on. Okay. I wanted to ask about the resources required for the sparse vector search. So let's say you have like a terabyte of logs. Is this going to run on my laptop, or do I need like a supercluster to do it?
Well, in this case, to do any kind of this stuff, you need the Elasticsearch machine learning nodes. I think the minimum requirement for it is 4 gigabytes of RAM. And I think it all depends. So this model is not very big, but I think it's doable locally. I didn't do it locally. I did it in cloud. So.
Any other hand? No? Okay. Thank you, Filip, for this.